Welcome guys, this is just a continuation of Science Paper 1 for the year 2023 for the internals. So the first part covered question 1 and 2 and we are starting from question 3. So the question reads, figure 3.1 shows an experiment on heat showing different materials connected to a trough of boiling water. An equal amount of wax and a small metal pin is attached to each material as shown. Right, so let's begin with the key. So the key tells us that the shaded part shows the wax, then the unshaded is showing us the distance of the area by which wax has melted. Right, so let's look at the first question. So the first question is identify the material where the meat will fall off first. So the answer is aluminium. Now, how did we know that we are dealing with, the answer is aluminium? We need to look at the distance from where the initial point was. So before the melting, the wax covered this area. So the distance from here up to here is greater than this distance, telling us that from the aluminium, a lot of wax was melted. So that's how the answer is. Then B, what was the aim of the experiment? So the aim of the experiment, we can just say to show that some materials are better conductors than others. Right, then question C, what can be concluded from the experiment? So we can conclude that aluminium is a good conductor. So let's put conductor here. So is a good conductor of heat. Then if you look at question D, give one use of good conductors of heat. For example, if you look at cooking utensils like pots in a kitchen, why most of that are they made from aluminium? So it's because aluminium is a good conductor of heat. So it's easy to conduct heat from the heat source into the things that are being cooked. So say cooking utensils. Such as pots, pans, etc. Right, we move on to question 4. So under question 4, Roman number 1, we just want to give a clear distinction between transverse and the longitudinal waves. So the difference that you can come up here is how the particles vibrate, for example, in a transverse compared to a longitudinal. So say in a transverse, so in a transverse wave, particles vibrates perpendicular to the direction of the wave, while longitudinal, meaning in a longitudinal wave, say particles vibrates parallel to the direction of the wave. So that's a difference. Right, so we move on to question Roman number 2. So a round object is dropped in a pond of water. Describe the shape of waves produced in the pond of water. So we are going to have a water wave, and a water wave is an example of a transverse wave. So say a water wave will be produced. Then we are saying this is a transverse wave, or if want we can say a transverse wave will be produced. Then we can add on this one. So let's say a transverse wave has a sine graph. So if we say a sine graph, we are looking at a shape like this one. So this is the shape that we are expecting to get after the dropping of this object in a water pond. Then for Roman number 3, if a vibrator produces 20 ripples of water which passes through a point in 10 seconds, what is the frequency of these waves? So there are two ways in which we can find the frequency. So let's first begin by finding period. So remember, period is denoted by capital letter T and defined as the time taken to make one complete oscillation. So formula is T over number of oscillation. So the time taken we are given is 10 seconds divided by the number of ripples was 20. So if we divide 10 by 20, we get 0.5 seconds, which simply means that for every 0.5 seconds, one ripple was produced. Now, how can we now proceed to calculate the frequency? We'll say frequency is equal to 1 divided by period, which is 1 divided by 0.5. So whenever you divide a number by 0.5, you just double that number. So this is same as the 1 times 2 is 2 hertz. This is our final answer. Or if you want, we can say frequency is equal to, we are just going to flip this formula where the n becomes the numerator while the t the denominator. So what is n? N is the number of waves, which is 20 over what's our t? T is the time taken, which is 10. So 10 into 20, we still get 20 hertz. 2 hertz. Right, we move on to question B. A boy standing in front of a building claps at intervals of 1 second. So we have a person here. This person is standing. Then we have a certain building. This is our building. So this person is clapping. Right, now let's look at what happened. So the echo produced coincides with the 5th subsequent clap. Calculate the distance between the boy and the building if the speed of sound in air is 340 meters per second. So the echo, the distance, we want the distance from here up to here. But for this person to hear an echo, the same distance must bounce on this building to the person. Now, we are told the echo was heard on the 5th clap, and for each clap, an interval of 1 second was done. So let's look at what is meant by an interval. So the interval simply means how much of something is in between. For example, if my final time is 2 and my initial is 1, the interval is the difference between the two, which is 2 minus 1 is 1. So for every second, there was a clap. But the echo was heard when he was clapping the 5th clap, which simply means that the first clap, 1 second, no echo. Second clap, no echo. Third clap, no echo. Fourth clap, no echo. Fifth clap, that is when an echo was produced. which simply means that it took 5 seconds from the initial up to the 5 to produce an echo. So we have at least time. So we'll say time is equal to 5 seconds. So if we have time, how can we find the distance? So we'll say speed is equal to 2d. Why are we putting 2d? There is the going and the coming. So whenever I deal with an echo, it's 2d over time. So over 1, we cross multiply, which is 2d is equal to speed times time, which is, let's say 2d is equal to, what's our speed? So speed is 340 meters per second divided by, what's our time? Multiplied by 5. So 2d is equal to, so if you multiply 340 by 5, so let's say 5 times 0 is 0, 5 times 4 is 20, so we write 0, we keep the 2, 5 times 3 is 15 plus 2 is 7. So we divide by 2, we divide by 2. So what is the half of 1,700? So I'm getting 850 meters. So this is the distance, which simply means that when going, sound took or covered the distance of 50 meters. 850 meters, and also when coming back 850 meters. Thus we have the total distance of 1,700. Then we move on to question C. A vibrating turning fork is marked 256 Hz. So this is the frequency. So we have been given the frequency. Calculate the wavelength of the sound wave that the turning fork produces, taking the speed of sound in air as that shown in B4. So the speed is equal to 340 meters per second. So let's look at the formula that we can use if given speed and frequency. So say velocity, which is same as speed if moving in a straight line, is equal to frequency multiplied by lambda. Now the question is the wavelength. So we are solving for lambda. So we are going to divide by frequency. Also here by frequency. So lambda is equal to speed over frequency. So what's our speed? 340 meters per second. What's our frequency? The frequency is 256. So 340 divided by 256. So I'm getting 1.328125. So 1.3 meters. Right, we move on to question. So we go to question 5. So figure B 5.1 shows a ray of light moving from medium A into medium B. Alright, so we have the incident, then we have the refracted ray. So if you look at refraction, it's all about the bending. So define refraction of light. So say this is the bending of light after striking a medium of different density. So what causes refraction is the difference in densities of the media. Which medium is denser than the object? So we need to focus where the bending occurred. So this is the bending, and we have the normal. So since the refracted ray was away from the normal, then the medium B is less denser. Now we want the media that is denser, so we'll say medium A. Then we have to justify our answer. So say because light bent away from the normal ray. So this is how we can answer a question like this one. So that's it for this video. Thanks for watching.